Hello, I'm Neeraj. Today I will try to explain the concept of variational autoencoder. Actually, these days, generative models are gaining a lot of importance. And variational autoencoder is also a generative model. It's very basic generative models. So we will try to understand that how such kind of models are working. When we provide some images of human, it generates a new images of human with some creativity. So what are the things which make such kind of models capable to do such kind of creativity? So for this, we will go step by step. First of all, we will go through the autoencoder, like how it is working. Then we will go through the variational autoencoder, how it is different from traditional autoencoder. Then we will try to understand that what are the factors which are responsible for those creativity which we so called like generative, which makes it a generative model. So let us start with autoencoder. Generally, all autoencoders contains three important parts. First is the encoder part, decoder part, and latent space. When we pass the image through the encoder part, which is actually neural network architecture that we can design through perceptrons, through CNN, and a lot of possible ways to design such kind of architecture. So once it pass through the encoder architecture, it extracts the features from the images. Features may be like shape, maybe edges, maybe context, and so many features are possible. And when we pass this information to next layer, it extracts the latent variable. So latent variable is like from these features, it extracts some values like x1 is equal to 0.5 for shape for one image, x2 is equal to 0.3 for context is equal to like 0.7. Such kind of feature is extract. Latent variables is extract. Now in the decoder part, the system use those latent variables to again reconstruct this feature, and from this feature the system reconstruct the output. It is assumed that the input image and reconstructed image both should be similar. So this is the ideal autoencoder. So in both cases we use some neural network architecture. Now to train such kind of networks, we need some cost function. So for example, here we have some neural network architecture, here we have some neural network architecture. So those neural network architectures having learnable parameters theta and phi. So loss generally we can calculate through mean square error. We can calculate through and cross entropy also, but it depends upon the requirement. Here for simplicity I will go through the mean square error. So in the case of mean square error, for every I image, suppose we have total n images, so for every I image we take this value and take this value outcome value like x at I and then calculate the mean square error. Now we can represent this xi through neural network way also. How we can represent this? So when we construct this feature, first of all we take the input, pass through encoder, all neural networks having learnable parameter theta, and we pass the input xi. So once we pass this, it generates the latent variable. So when we pass this latent variable to decoder part, this is another neural network that is represented by G5. Another set of neural network, not just neural network. This is also a set of neural networks that may be a combinations of perceptrons and CNNs or anything. It depends upon your requirement. So we just say that phi is a set of all learnable parameters. Then it will generate xi hat. So this xi hat I used here. So this is a simple case. So why this is a simple case? Why it cannot generate a new kind of creative images? Because here when we take the images, it generates a fixed set of latent variables. Here you can see the values, and the decoder part use those latent variables and reconstruct the input. So we don't have any scope to do anything. Now we will try to understand it, how variational autoencoder is different from traditional autoencoder. So what happens in the variational autoencoder? We take the input images, because here everything is related to probability and everything. So from starting we consider that we have identical independent distributions IID of images. We pass those images to probabilistic encoder, not like a traditional encoder, probabilistic encoder. We will explain in later that a lot of this looks very straightforward, but it is not so straightforward. So we pass it through probabilistic encoder. Probabilistic encoder generates the mean. Probabilistic encoder actually extracts the features from the input images. Again, features are similar, like age, shape, context, kind of things. But instead of generating such kind of latent variables, it generates the mean and variance or standard deviations. Combinedly, for all those means and standard deviations, we say it like a multivariate Gaussians, represented as Z, Z mu and Z sigma. And from these Gaussian multivariate Gaussians, we extract the sample that is known as sampled latent variable. So this sampled latent variable is different from these fixed things, and the decoder, probabilistic decoder part, use this sampled latent variable to again reconstruct the features, generate the features, and from those features we get the image which are, we assume that both are similar. So this is the process. Now, as I said earlier, the entire process is not so straightforward. The first part is probabilistic or encoder. We, instead of calculating the latent variable, we are computing some normal distributions or Gaussian distributions, some distributions, probabilistic distributions, normal, Gaussian. In the case of Gaussian distributions, in the case of gamma distributions and similar kind of distributions, it is very tough for any Bayesian kind of probabilistic distribution, probabilistic encoder or probabilistic technique methods to directly generate such kind of things. It is known as totally intractable, means calculating probability of Z, means probability distributions of getting Z given X, means latent variable Z for given latent variable distribution Z for given X, is intractable. Means through a finite time, through a finite system, it is almost impossible to extract or near to impossible to extract. So in that case, what we do, as I said, it is not straightforward. So we assume that we have some probability distributions. We have some probability distributions Q which achieves the sample latent variable Z for a given X, that we achieve through some neural network architecture. Means we assume that similar things we are achieving through, instead of probabilistic encoder, we are achieving through neural network, some neural network architecture combinations. We are achieving this, and we representing this as a different probability distributions. Now, if we go like this, then it will totally destroy the system. So what we do, we try to minimize the differences or distances between both distributions so that it can generate the similar kind of sample latent variable that for this we are assuming that it will generate. For that we use the scale divergence, and we minimize the scale divergence between the taken and this given probability distributions. So this is one important part. So during the training, our task is to minimize this scale divergence, so that when our neural network architecture, which we develop in place of this probabilistic distributions, probabilistic encoder, it will learn the similar kind of sample latent variable. So we use this kind of scale divergence, and we use a simple similar kind of things. We just after some derivations, we generally got this kind of scale divergence, which are nearer to like Z. Means suppose we have a prior distributions, we assume that we have available prior distributions of Z, so it should be similar. So now this problem is solved. Now another problem is how the system can get some creativity to behave like a generative model. So this is hidden in these steps. So what happens in the traditional architecture of autoencoder, like this? Here I have just discussed, like in the place of latent variable, it creates a fixed set of variables. For example, this is a fixed set of variables, -2, some values are there. So this is a single point. So by using this single point, we will have a limited scope to generate reconstruct the same image only. But in the case of variational autoencoder, as I said, instead of latent variable, like I discussed here, the system generates mean and standard deviations. This provides us freedom. So for example, if this is a mean, then this distance will be represented by standard deviations, and all the points surrounding those means will have a very high similarity with respect to this mean, and the sample latent variable will select the point from this area, means surrounding the mean. For example, here we have just a fixed option to select one point, but here we have a lot of options to select points near to the mean and inside standard deviations. Then in the sampled variable, we get a lot of chances to get some creativity, to add those creativity in the images. Now other thing is like how it actually works. So how we generally select those kind of things? For that, generally we use reparameterization techniques and Monte Carlo simulations, etc. Once we get some derivations for loss functions that we will describe in the next part. So for the simplicity, I will just give the overview that how it is working. So here it is clear that instead of single point, where we have a lot of points that we can select surrounding the mean, and it gives the creativity, chances of creativity to variational autoencoder to generate the nearly similar kind of images with some creativity for any new images for the trained variational autoencoder model. Now, how we achieve this? So, you will understand it from here. Once the system generates the mean and standard deviations, and we take it like a multivariate Gaussian distributions, to calculate the sample latent variable, we take the mean plus standard deviations into element-wise product of psi. That psi is a unique normal distribution. So the role of this unit normal distribution is to adjust these standard deviations in such a way that it will not go far from this mean point, and image will have a lot of similarity with the original images, means it will not create a totally dissimilar things. So it means it controls such kind of similarity related things. Means it ensures that the latent variable distributions, this sample latent variable distribution should be close to the standard normal distributions. So here you can see that this is the latent distributions that is coming through Z mu and Z sigma. It is I just explained through two-dimensional things, but it is actually three-dimensional. So just consider that it is three-dimensional. So now unique normal distributions mean 0 and standard deviations 1. So once we take the point-wise product, element-wise product, then we can and add it with mean, then we achieve this sample latent variable. So next part is the decoder, probabilistic decoder use the sample latent variable to reconstruct the features, same type of features. So it reconstructs the features, and then as a later stage it reconstructs the image. Now the issue is the reconstructed images. Once we train the model and if we pass a new image, due to these kind of things, the system will be capable to add some creativity on those images and work and behave like a generative models. Now, like autoencoder, as I earlier discussed, like we need some proper loss function to train the system. So how we can define our loss function? So actually here loss function has two components. Here loss function has one component because everything is straightforward. So we just take the reconstruction loss. Like suppose we constructed x hat from x, then we take the mean square error and then calculated the reconstruction loss. But here also we have a reconstruction loss part. But we have another loss part also available. So when we try to generate, then we use another neural network architecture that we assume that instead of traditional probabilistic encoder, that will generate a traditional similar kind of distributions, and for that we use the scale divergence loss. So the entire loss is a combination of reconstruction loss plus scale divergence loss. In the later section of part of this tutorial, I will try to explain that how the variational inference part actually work, and we will try to derive the equations for variational inference part, which is very important and responsible for all the generative process.